Now we move on to the last part of the chapter, density and pressure. This one is just something very simple. Okay, density is just mass per unit volume. You've all learned this before. The symbol of density is rho. You take mass divided by volume. Now density is constant for a given material. Now what do I mean by this is it can be interpreted as this. A material cannot have different values. Sorry, the same material, maybe I should write this. The same material cannot have different values of densities. What I mean by this is that if I tell you the density of copper is maybe 1,500 kg per meter cube, if I have different, if let's just say I have something like this, and then something like this, and then some other funky looking shape like this, and I tell you all of these are made out of copper. Okay, since they're all made of the same material, it doesn't matter what shape they are. The density for all three of these objects will be the same. Okay, that's what I meant by this statement. Density is constant for a given material. All right. In other words, the same material cannot have different values of density. It will always be same. It will always be the same for a given material, which is basically this statement here. All right. So if let's say you have some object, a sphere, a cube, and some sort of prism, they're all made of the same material, say copper, the density will always be the same. Okay. This density will be the same as this density, will be the same as this density. They will not be different. If you change to a different material, say maybe steel, then yes, your density will change. But as long as you're using the same material, the density for the material itself will always be the same. Okay. Now, there are some cases also where we will tell you that you mix certain substances together with different densities. And then we ask you to find the density of the resulting mixture. Now, to find the density of the resulting mixture, you should never ever use the average of the different densities. What do we mean by that is that if let's say you have a beaker here right now, and then you have a mixture of substance with density rho 1, rho 2, or rho 3, you have say 3 different liquids. Okay. You have 3 different liquids, rho 1, rho with densities rho 1, rho 2, rho 3. You mix it up. This is your mixture. If you say that the density of the resulting mixture, the average density is rho 1 plus rho 2 plus rho 3 divided by 3, this is wrong. Okay. If you mix different substances with different densities and we ask you to find the average density of the resulting mixture, you should never ever do something like this. Okay. Instead, what you should do is that you will have to do this. You will have to find out what is mass of liquid 1 plus mass of liquid 2 plus mass of liquid 3 divided by volume of liquid 1 plus volume of liquid 2 plus with volume of liquid 3. This is actually total mass over total volume, which is what you get here. Okay. When it comes to finding densities of different substances added together, always use this formula. Okay. It's actually a modification of this. Just change the mass to total mass, volume to total volume. Don't ever use this. This is wrong. Okay. This is the correct one. Okay. So this is for density. And then the next thing we move on to is pressure. Pressure, you should already know also before this. Now, pressure is force acting normally per unit area. Okay. The emphasis here is that you need to have the word normally. This is the word normally here, it means perpendicular. Okay. It is a force acting perpendicular to the area. Okay, force acting normally per unit area, force acting perpendicularly per unit area, perpendicular to the area. Okay, so pressure is force over area. Now you need to know how they derive pressure equals to H rho G. Pressure is force over area, but pressure can also be H rho G. Specifically, you have learned this as the pressure exerted by a liquid at a certain depth. So this particular equation here, the derivation is required to be known. They expect you to know how to derive P equals to H rho G. It's actually derived from this first definition. So how do we get that to here? So if pressure is equals to force acting per unit area, and you want to find out the pressure exerted by a liquid, let me just clear off everything here. If you want to find out the pressure that is exerted by a liquid, let's just say right now you have a column of liquid like this. You want to find out what is the pressure at the base of the column of liquid. Okay, the pressure at the base of that column of liquid is actually due to the weight of that column liquid acting down over the area. Okay, so if I ask you right now to find out pressure caused by a certain column of liquid, it's actually caused by the weight acting over the area of the liquid. So pressure, you know, is force over area. The force right now is the weight of the column of liquid. The area right now is this area. All right. The weight is mg. Okay. The mass of the liquid multiplied with gravitational acceleration, and then you know that density is mass over volume, where mass is rho v. So you change it to rho v here. Eventually, you get rho vg over a. Now, volume is actually equals to area times height. You may not be able to see the area here because I wrote something over it. If you take the area multiplied by the height, you're going to get volume. So over here right now, there's one step missing here. You can actually say that rho is AHG divided by A. The A will cancel, giving you H rho G. So pressure exerted by a liquid is actually equals to H rho G. Okay, so there's one part here that you can see. Pressure is actually equals to H rho G. All right, now from here, you can also see a few things. Let me just clear off everything. You will see that pressure is actually proportional to height, or rather your depth. Pressure is also proportional to your density. So what this means is that if H increases, pressure increase. This also means that if your density increase, your pressure increase, which is what this thing is trying to tell you. Pressure in a liquid increases with depth below its surface. It's talking about this. The larger your depth, the larger your H, the larger your pressure. Okay, pressure in a liquid depends only on the height of the liquid and not on the shape and width of the tube. If let's just say right now I have a liquid that is contained inside 4 different containers, this, and this, notice that they're all of different shapes and volume. If I'm interested to find out what is the pressure at the bottom for all those liquids, because they share the same height, same depth, same row. Maybe I write it here. Sorry, this is a bit messy. Maybe I write here. Because they share the same depth, same row, therefore pressure is the same. Okay, so right now you see for the 5 different containers, A, B, C, D, and E, they have the same liquid, same row, they have the same height. If I ask you what is the pressure at the bottom, the pressure is always going to be the same. That's why here this statement says that the pressure in the liquid depends only on the height of the liquid and not on the shape or width of the tube. It won't affect anything. It only depends on the height as well as the density. Okay, so that one is okay. So the other part here, pressure in the liquid is proportional to the density of the liquid. That one is given here. You can see that P is proportional to rho. All right. Now pressure in the liquid is equal in all directions at the same depth. This one just means this. If let's just say that this one is a certain height, maybe I draw something here. The part where they say pressure is equal in all directions at the same depth, it just simply means this. If this is the object, if let's just say this is a liquid, I have an object that is submerged here. This part here is at a certain depth h. Now, at this particular depth, you will have pressure. Pressure acting something like this. Okay, this part here, if let's say you have an object that's submerged inside a liquid, if you're talking about a particular section at a certain depth, that particular section here will experience pressure of the same magnitude in all directions. This is a 3D view of it. If I tell you, if I give you a 2D view of it, it's just something like this. Basically, at that depth h, your pressure here acting at this particular section itself, it will be in all directions and it will be equal. Okay, if we this one we tell you is 10 pascals, this one will be 10 pascals, this one will be 10 pascals, this one will be 10 pascals. Okay, it's equal in all directions. All right, so that's what this one means. If you're talking about the same depth, the pressure is always the same at that point. All right. Okay, the last thing that I just need to go through with you is how to calculate pressure given a manometer or barometer. All right. Now, right now, barometer and manometer are just some things that you use to measure pressure. All right, but you're required to know how to calculate pressure out of it. So let's go through that. All right. So right now, let's just say you want to find out the pressure given by this barometer here. We tell you that this cylinder, closed cylinder here, has a vacuum inside. So the pressure is actually 0. Okay. You want to find out what is the pressure of your atmosphere right now. Basically, just think of it this way. Whenever you encounter questions like this, you look at your reference depth. This is your reference depth. Okay. At the same reference depth, the pressure for the same liquid is always the same. Okay, this is one statement that you just need to know first. The same reference depth. Sorry, I missed out the word reference. Okay, at the same reference depth. Okay, at the same reference depth, the pressure for the same liquid is always the same. So right now, this one is your reference depth that has the same liquid. So if I tell you I consider 2 points, point A and point B, I can say that pressure at A for that liquid is the same as pressure at B for the same liquid. Now, pressure at A is caused by the pressure of your atmosphere. Pressure at B is caused by the column of liquid above it. So the pressure due to a column of liquid, just now you learned, is H rho G. So you're gonna get this. This is basically what this one is. All right. Pressure of your atmosphere is equals to H rho G. Now, if let's just say you had the same thing again, same apparatus set up again, but this time you do not have a vacuum. You have some other gas here with a certain pressure. Say now you have the same apparatus again, all right? But right now you have some gas inside, okay? It's no longer a vacuum. This one has a certain pressure, okay? This one also has a certain pressure. Your pressure of your liquid equals to H rho G. Now, you look at your reference depth again. This one is your reference depth. Your reference depth must always be for the same liquid. Okay, this one is your reference depth again. Now you consider point A and point B, you will still come to the same conclusion that pressure at A is equals to pressure at B for the same liquid for the same reference depth. Pressure at A is due to the atmospheric pressure. Pressure at B is due to this, the pressure of the liquid and the pressure of the gas. So it will be P of the gas plus P of the liquid, which will be P of the gas plus H rho G. So this is what you get, okay? This is how you get this thing, all right? For questions that involve barometer, manometer, you will always find the reference depth first and then equate the pressure. All right, so now you go to the last example here. This one is a manometer. The manometer has a U-shaped thing to it. So right now, if I want to find out something and I want to solve questions that involve a manometer, same thing as before, always consider the pressure at the reference depth on both sides of the manometer. Right, I wrote it here already. Okay, consider the pressure at the reference depth for the liquid on both sides of the manometer. The pressure at both sides is going to be the same at the reference depth or height. So right now, what do I mean by the reference depth? The reference depth is this one. This is your reference depth. Always choose the one that is for the same liquid. And also choose the depth where the liquid is going to change to something else. You see, this part here is actually the liquid and then changing to gas. You normally take this part here before it starts to change to something else. Okay, so this part here is your reference depth. Same thing as before. I can say that if I consider point A and point B here, pressure at A is the same as pressure at B. The pressure at A is due to the pressure of the gas. The pressure at B will be due to the pressure of the liquid, which is equals to H rho G, and also pressure of the atmosphere. So pressure at B is pressure of atmosphere plus H rho G, giving me this. Okay, so this is how you will do it. For questions like this, always find the reference depth. Page 6, question 19. All right. Now you have a U-tube that is closed at one end that contains mercury. Air pressure of 5 times 10 power 4 Pascal is trapped at the closed end. The other end is open to the atmosphere and is fitted with a piston of mass 5 kg and cross-sectional area of 5 times 10 power negative 4 meter square. The density of mercury is 13,600 kg per meter cube and atmospheric pressure is 1.01 times 10 power 5. What is the height h of the mercury column? All right. Now, questions like this I mentioned to you just now, always try to find the reference depth and equate the pressure on both sides. So your reference depth is actually this one. Okay, the reference depth must always have the same liquid on both sides, on either side of the point that you're considering. So right now, this is your reference step. You consider pressure at point A and pressure at point B. Now, pressure at point A is going to be the same as pressure at point B. All right, because they're the same liquid, same height. So what you do is that you find out individually what's the pressure at A, what's the pressure at B. Now, pressure at A is due to the atmospheric pressure, because they already told you that this part is open to the air, right? They told you here the other end is open to the atmosphere, and the atmospheric pressure is 1.01 times 10 power 5 Pascal. Your atmospheric pressure, and you also have the pressure due to the piston. So pressure at A is pressure of atmosphere plus pressure of piston. And then pressure at B will be the pressure due to the liquid and the pressure of your air here. Okay, so this one will be pressure of the liquid plus pressure of the air. So what you then do is that you try to expand what you have here. This is pressure of atmosphere. The pressure caused by the piston will be equals to force over area, or in other words, weight over area. Okay, which in turn is equals to mg over area. So this one is mg over area. The pressure of the liquid is h rho g. The pressure of the air is what you have here. And so what you want to find is h. The rest is something that you know. So what you do is you just submit all the relevant values. Pressure of atmosphere would be 1.01 times 10 power 5 plus with mg 5 kg times 9.81 divided by area of 5 times 10 power negative 4 equals to h. Density is 13,600 times 9.81 plus with trap pressure 5 times 10 power 4. So try to solve this. You should get the answer as 5 times 9 divided by 10 power negative 4 plus 1.01 times 10 power 5 divided by 5 times 10 power 4 divided by 13,000. You should get your answer as 1.12 meter. Change to centimeter, it will be 112 centimeter, but this is 3 SF. You change to 2 SF, is 110 centimeter, isn't it? So your answer should be D. Okay, so this is one part here. This is the height h of the mercury column. All right. Okay, so that should be it for today. Next week, I'll probably just take 1 more hour to discuss more questions about this chapter with you. And then after that, the other hour, I will go on to your work, energy, and power. Okay, this one is just for next week. The first hour, I'll just do your past year question. I need to do more examples for your current chapter. And then the remaining 1 hour, I'll do your work, energy, power. All right, so that should be it for today. Do you guys have any questions? If you don't have any questions, then that should be it. Have a very nice dinner and have a great weekend. It's already 12th November. All right. Your exam is in another 2 weeks. Okay. By the time you go for your exam on 29, yeah, we've already finished your work, energy, power, and done some examples on that. But if you want to be really more prepared, I would suggest you do more and more questions for your past year. And any questions that you have, just let me know. Then after that, I'll answer it for you separately. Either I'll make a recording to answer it, or either I'll just answer it through WhatsApp for you guys. Right, that's it. See you guys next week. Yep, okay, thank you. Yep, see you guys. Enjoy your weekend. Right, have a great week too. Bye. Okay, right, okay. The question says that you have a W-shaped tube that contains two amounts of mercury, each open to the atmosphere. Air at pressure P is trapped between them. The diagram shows two vertical distances x and y. Okay, the trapped air that they're talking about is this pink colored portion that I highlighted. And then they say that each end of the tube is open to the atmosphere. It is referring to this part and this part. Okay, so the pink color portion here, the middle portion here, the trapped air had a pressure of P, whereas the other end that's exposed to the atmosphere had atmospheric pressure. Okay, so right now what the question wants you to do now is that they say that the atmospheric pressure is equal to the pressure that will be exerted by a column of mercury of height 760 millimeter. The pressure P is expressed in this way. So right now what they're saying also is that rather than expressing pressure in pascals, they're expressing it in terms of heights. Okay, in specifically right now they say the atmospheric pressure is equivalent to a mercury height of 760 millimeter. They are now asking you, based on the answer choices that you have here, what values in x, y, and p are possible. All right, so when it comes to analyzing questions like this, any kind of question that involves something like a YouTube, always try to find the reference depth or reference height, and then try to work out an equation for both ends at the of the reference height. So right now, what you can do is that you can actually split this tube into two parts. You can split it into half, okay? So that this one is one YouTube, this one is one YouTube, okay? And then from there, what you want to do is that you want to find a reference depth that you want so that you can work out some sort of equation. So for the left-hand part here, your reference depth could be this one. This is your reference depth. So recall that last week I mentioned to you, your reference depth must have the same liquid on both sides. So this one is a suitable portion for it, where you have the same liquid on both sides. And one of it is just about to go to something else. All right, this is the first reference depth. Your second reference depth on the other end, sorry, your other reference depth on the other end could be this one here. This is your other reference depth. Okay, so you have two reference steps. So let's just say, for example, I label these points. There's point A here, and there's point B here. For this reference step, pressure at A is equals to pressure at B. Now the pressure at A here will be equals to the pressure due to this column of liquid and the atmospheric pressure. So I could actually just write this as X plus atmospheric pressure 660 millimeter. Recall that just now the question below, the description of the question below here mentioned that the pressure is supposed to be measured in terms of height. So we need to measure in terms of height now rather than Pascal. So everything that you see here for the pressure is actually measured in heights, in terms of height. That's why I use X and I use 160 millimeter. So the pressure at B, on the other hand, that you see here is going to be the pressure due to the trapped air. This one is just going to be equals to P itself. Okay, so this one is one equation that you have. Now, if you move on to the other tube, the other portion of the U tube, you do the same thing. Equate the pressures at the reference depth. Let's say this is point C, and then this is point D. So I could say that pressure at C is equals to pressure at D. Now, pressure at C is the pressure due to the trapped air only. So this one is going to be P. But the pressure at D is going to be the pressure due to this column of liquid as well as the atmospheric pressure. So this one here, if I specifically, it may not be that clear right now with so many things written on the screen. I want this height specifically, okay? But what I have here is not directly written. So you have to deduce out what is this length here. The way to deduce that would be, you see you have the length 50 millimeter here, and then the length y here. This one will actually be 50 minus y, okay? So pressure at D is actually the pressure due to this portion here, which is actually 50 minus y, plus with the pressure due to the atmosphere, which is 760. So you try to simplify this, you're gonna get P equals to 810 minus y. Okay, so you have two equations here. I'm just going to rewrite the equations on the right hand side here. So you actually have two equations that you can refer to. X plus 760 equals to P, and then 810 minus y equals to P. Okay, so for the answer choices that you have here, what you just want to do is that you try to see which of these answer choices, the A, B, C, and D question, the answer choices A, B, C, and D here that you have. What you want to do now is that you want to see which combinations given here fully satisfy both of these equations. So this one you have to do something like trial and error. So let's just say, for example, I go with A right now. I want to see whether all these given values satisfy both of the equation. So what I just want to say here is select answer. Okay, maybe I'll just rewrite this here. Correct answer is the one that satisfies both equations. Okay, so what you want to do now is that you look at each of these answer choices, see which of these actually satisfy both of the equations that you have actually gotten here. All right. So say I choose A right now. If X is 20, then plus with 760 here from the first equation, I'm going to get 780. Okay. But if I look at Y right now, 810 minus 20 gives me 790. Okay. So you will see that if I just look at answer choice A, when X is 20, plus with the atmospheric pressure, it will give me P. So right now, X is 20, P is 780. I'm getting that here, okay? But then when I try to shift to Y here was 810 minus the, yeah, here is, I think this is self-explanatory. I don't need to write anything. So if I choose Y as 20, I put it inside the second equation here, 810 minus 20 giving me 790. There's something wrong with the P that I get here. You see the P that I get here is 790. It is already different from what you have in the first equation and is not the same value as what is written here. So this one doesn't, something is wrong with this. So answer choice A is out. Okay, it doesn't satisfy both equations. Now, if you repeat the analysis for the second answer choice, say B right now, when X is 20 plus with 760, I'm going to get 780. So X is 20, P is 780. This one seems to be okay right now. But if I go and choose for Y equals to 30, I'm going to get 810 minus 30 equals to 780. So Y is 30, P is 780. Now you see these two are now the same. And it is also the same as what you have written inside your table here. So this one actually should have been the correct answer. Answer choice B here is the correct one. Now, if you repeat your analysis for C and D, needless to say, C and D is also wrong. You can do this later on. Only the ones that satisfy both equations is this one. And B equals to, the answer choice is B. X is 20, Y is 30, and then P is 180. Okay. So this is how you would do this one. Okay, so if this one is okay, then I move on to the next page. Okay, the next page, you will see that the diagram and the equation is somewhat similar to what you've done in the notes. It is actually the same thing, okay? I actually make use of this inside the notes, but I'll just go through it very quickly for you. There's some portions here that we did not go through that wasn't inside your notes. Okay, just look at the next page. Okay, right. A rod PQ is attached at P to a vertical wall as shown in figure 3.1. The length of the rod is 1.6 meter. The weight W of the rod acts 0.64 meter from P. The rod is kept horizontal and in equilibrium by a wire attached to Q and to the wall at R. The wire provides a force F on the rod of 44 Newton at 30 degrees to the horizontal. So this part here, they're just asking you find out the vertical component of force F and the horizontal component of force F. So force F is this part here. They want the horizontal and vertical component. So this one, the horizontal component, this one, I think the horizontal component. Fx is the horizontal component. This component is adjacent to angle 30 degrees. So this one should be F cos theta. In other words, it should be 44 cos 30. The vertical component of force, if you shift it to complete a triangle here, it is actually opposite to the angle 30 degrees. So this one should be sine, okay? So Fy equals to F sine theta 44 sine 30. So the answer you get would be something like this. All right. Fy would be 22.0 Newton. Fx would be 38.1 Newton. Okay, so it's for this and it's for this. All right, then for part B, they ask you by taking moments about P, determine the weight W of the rod. Okay, so in the previous, for the same example, inside your notes last week, I went through a bit about why do we pick certain points for the pivot. So you generally tend to pick a point where an unknown force passes through so that you don't need to consider inside your calculation. Here, the question actually has made it simple for you. They tell you specifically which point to take. So they ask you take moments about point P and then determine weight W of the rod. So there are actually three forces acting on the rod right now. The first one being force F, the second one being weight W, and the third one being an unknown force P here. But right now, the question specifically asks you to take this as your pivot. So this force here is not considered under your moment calculation. All right. So taking moments about P, you should know that we've gone through this example already. So I'll just go through it quickly with you. So taking moments about P, sum of moments is equals to 0 because object is in equilibrium. Because object is not moving, therefore in equilibrium. So if something is in equilibrium, there were two conditions. Sum of forces in any direction is, there's no resultant force in any direction. There's no resultant moments about any points. So this one is where you get your sum of moments equals to 0. So the one I taught you that day was take moments about some point here is take moments about P and then set some sort of sign convention. And from there, you start to sum up your moments. All right. So from what you can see here, there are actually only two forces that you need to consider. This one, as I mentioned, you don't need to consider already. You only need to consider this and this. All right. Now, weight W will cause a moment in this direction. It's in the direction of your sign convention, so it's positive. Fx, you notice that if you extend the line of action, it will pass through the pivot. So this one again is also not considered. The only one you consider is Fy, and the perpendicular distance is this. All right. This one will be 0.64 plus 0.96, giving you, I think, 1.4 meter. Sorry, 1.6 meter. Okay. This one, you notice that it causes a rotation anti-clockwise. So this one is negative moment. Okay. So when you add it up, that's why you get something like this. W times 0.64 minus the vertical force times 1.6 equals to 0. Then eventually you get your weight. Now, when we say sum of moments equals to 0, it can also be interpreted as clockwise moments equals to anti-clockwise moments, because some teacher may teach you something like this also, or you may have intuitively used this also. You see, when we say sum of moments equals to 0, it can also mean something like this, where we tell you that clockwise moment, maybe I use a different color, sorry, where we tell you clockwise moment equals anti-clockwise moment. Maybe I get rid of this. Okay. When we say resultant moment about any points is 0, no moments about any point, it means this clockwise moments is equals to anti-clockwise moments, so that they cancel off. Likewise, you can also say this. When we say sum of Fy forces is 0, it means outward force equals downward force. And if we say sum of Fx forces is 0, it means right force equals to left force. Okay, so sometimes when you do your questions on equilibrium, you may have been using this understanding in doing the questions. Is actually correct because they're all derived from this in the first place. Now you look at the equation that is written here just now. Let me just scroll down a bit. This portion here, you notice, is actually your clockwise moment. This portion that you see here is actually your anti-clockwise moment. Now, you see you have a negative here. If you try to shift it around, eventually you get something like this. W is 0.64 equals to 22 times 1.6. You see, when you do it this way, this one is already telling you clockwise moment equals anti-clockwise moment. Okay, so when you do your questions, sometimes you may start it like this, sometimes you may start it like this. It really depends on which one you are more comfortable with. Some students tend to prefer this one more. For me, I tend to start with this. All right, but if let's just say you don't really like this idea where you go and see positive, negative, you want to dive straight into which one is clockwise, anti-clockwise, then you can use this straight. All right, so your answer for this question is 55 Newton. All right. Okay, so from there, let me just clear off something. All right, we go to the next question. Now explain why the wall must exert a force on the rod at P. Why must there be a force on the rod at P in the first place? Okay, now because of just now I mentioned to you that there's an unknown force P here. Okay, right now that question is asking you to explain specifically why is there a force here. Now, if you recall back, what was your weight? Your weight is 55 Newton. Your force F here is 44 Newton. You can resolve it into Fx and Fy. Fx is 38.1 Newton. Fy is 20 Newton. Okay. Now, the beam is already known to be in equilibrium because it doesn't move. That would mean that sum of Fy must be 0. Sum of Fx must be 0. So as I mentioned to you, that would mean that outward force equals downward force, or rightwards force equals leftwards force, and so on and so forth. So right now, if you just consider the forces that you have here, you don't bother about this portion first. If you consider just the forces here and here, are the forces balanced? I mean, is there a resultant force being 0 in both x and y direction? Now you just consider the vertical forces first. You have 22 Newton force outwards, and then you have 55 Newton force downwards. You see, this force is not equal and opposite to this force. There is actually, if you just consider these two forces alone, there's actually a net force downwards, which is equivalent to 33 Newton. Okay, but the beam is in equilibrium. So this F net downwards of 33 Newton caused by this force and this force must have been balanced off by another force somewhere. So this can only be true if there is a force here. So your rod here has a force exerted on it that is 33 Newton upwards. This force will balance these two forces, giving you zero vertical force. Okay. This one is to explain why is there a vertical force at P. You can also do the same explanation for the horizontal forces. If you look at Fx, Fx is 38.1 Newton. This is the only horizontal force. But again, because your object is in equilibrium, sum of horizontal forces must be zero. The only way that this one can be having a zero horizontal resultant force is if there's another force at this point at 38.1 Newton acting opposite to what you have here. Okay, so therefore this point must have a force. Otherwise you cannot balance because you already know the condition here is in equilibrium. Horizontal forces is zero, vertical forces is zero. If you just consider the forces here, you're not getting sum of horizontal force equals zero, sum of vertical force equals zero. Something else must be present to make it all zero. So the only way it can be zero is if there's a force here. So the answer choice that you have here is actually explaining it either way. So they say that F has horizontal component that is not balanced by Y. Okay. F has 38 Newton acting horizontally, which should be an equal opposite force from the wall. Or you can also do this now. Let me just, if you just look at the statement in the red, if you just look at the statement that's written in red pen, I think this one is a better way of looking at it based on what I just explained. The vertical component of F does not balance W. F and Y do not. This one is just worth one mark. Oh, okay. You can either just say that the vertical component of F does not balance W, therefore there must be a force at P. Or you can also say that F and Y do not make a closed triangle of forces because you see W is just this, F is just this. So recall that for equilibrium, you must have a closed vector diagram. So if you only have this force and this force, you can never make a closed vector diagram. You need to have another force so that you can make a closed vector diagram. Okay, so these two are actually two separate answers. Either is answer choice 1 or answer choice 2. All right. The long-winded one is the one that's written in pencil here. Okay, but this one, F has horizontal component that is not balanced by W. That's correct. This one is talking about the horizontal component force. The 38.1 Newton that's not balanced by W. So that horizontal component is 38 Newton acting horizontally. There needs to be a force to balance it. That one should be an equal opposite force from the wall. Okay. Yeah, this is very long-winded way of talking about the same thing. I think you just take either this one or this one. All right. This is actually the same thing, just that I'm talking about the horizontal part. All right. Okay, for part D, on figure 3.1, draw an arrow to represent the force acting on the rod at P. Label your arrow with the letter S. Okay, so this one we actually did it already last week. So what I mentioned to you is that if something is in equilibrium, all the forces will tend to intersect at one common point. So for weight W, if you extend the line of action, it's like this. Force F, if you extend the line of action, is like this. They seem to intersect at this point. The unknown force at P must therefore intersect at that same point in order for your rod to be in equilibrium. So you just draw a ruler, use a ruler, try to draw the green line and pink line first, see where is the intersection point, and then from there you draw the arrow from P. Okay, label that arrow as S, and you get your answer. Okay, so that one is okay. All right, then we move to the next page. Okay, now November 15 P11, this one is page 6, the same, it's under the same page that you're looking at. Now, in which example is it not possible for the underlying body to be in equilibrium? Okay, they give you four answer choices. Which of this is not possible at all to be in equilibrium? Okay. Now, when we say that something is in equilibrium, the thing that commonly comes to mind is that sum of force is 0, sum of moments is 0. Now, specifically, when we take sum of forces equals to 0, that would mean that there's no acceleration. Okay, because when we say that sum of forces is 0, it means no resultant force, no acceleration. Okay, this one was basically saying to you no resultant force in any direction. If there's no resultant force, by right, you should have no acceleration. So you look at each of these answers one by one. Okay. Now, if you have an aeroplane that climbs at a steady rate, say answer choice A, you have an aeroplane that's climbing at a steady rate. Steady rate here means constant velocity. Okay, so V is constant. Okay, constant V. So since you have constant V, this one can be equilibrium. Okay. Now you see, when we say something has no acceleration, based on what you've learned under kinematics, when something has no acceleration, it implies constant velocity. Okay, so when they say that the aeroplane is climbing at steady rate, it implies constant velocity. Constant velocity implies no acceleration, which then implies no resultant force. Therefore, it should be in equilibrium. It can be in equilibrium. Then the next one is an aeroplane tows a glider at constant altitude. Okay, so for answer choice B, what they're saying now is that you have a glider that's being towed by some sort of aeroplane right now. Okay, this is your glider. They say that it is at constant altitude. Basically, it's just same height throughout. Okay, this one is same height throughout. It is neither climbing up, neither climbing down. Now, when they say that the aeroplane throws the glider at constant altitude, they never say anything about whether there's an acceleration or constant velocity here, right? So here, this one, if we say that there's acceleration, this one can be true. If we say that this, sorry, my handwriting is pretty horrible. Let me just rewrite it. If you say that it has acceleration, that is possible. But if you want to say that it has constant velocity, it's also possible. Okay, so here, if I just tell you an aeroplane tows a glider at constant altitude at same height throughout, you could say that it could be either having an acceleration or it could be moving with constant velocity. Both cases apply. But the question here says, which is not possible. All right. For the case that you have here, if it is constant velocity, if plane was moving with constant velocity, is possible to be in equilibrium. So the answer choice B here, where they say an aeroplane throws a glider at constant altitude, it can be moving it with constant velocity. So therefore, it can be also in equilibrium. When you have constant velocity, as I mentioned, no acceleration, no acceleration means no resultant force. No resultant force means constant. Sorry, no resultant force means equilibrium. So this part here, B can also be in equilibrium. The keyword here is possible to be in equilibrium. They didn't give you the full information. They just want to know, is it possible? All right. Yes, possible if it was moving with constant velocity. Now, if you look at answer choice D, this one is also something similar. Also, two tugboats tow a ship into the harbor. It would be talking about something like this. This is your ship, and then it's being towed by two tugboats like this. So same thing again, they didn't really mention anything much about this. It could be that the two tugboats were towing your ship into the harbor with a certain acceleration, or it could also be a case where they were towing the boat into the harbor at constant velocity. Okay, either case is possible. The question never specifically mentioned which, but either case is possible. So since it is possible to be having constant velocity also, it is possible to be in equilibrium, just like answer choices A, B, and D. Okay, so that leaves us only answer choice C. Answer choice C is not possible to be in equilibrium. Okay, this one is not possible to be in equilibrium. Why? The thing here is that, yeah, they say here constant speed, all right? But this one is not constant velocity, you see. What they say here is that a speedboat changes direction. The keyword here is change direction at constant speed. If I give you an example, this one is related to what you learned in the previous chapter. If let's just say your boat is moving in a circle. Wait, I ran out of space. Let me just clear this one off. Can I draw it down here? If this is your boat, and then it moves in a circle, all right? So this one is 10 meters per second. This one is 10 meters per second. This one is again 10 meters per second. And this one is also 10 meters per second. This one is this case here. You have a speedboat that changes direction at constant speed. You see, this speedboat is continuously changing its direction, but the magnitude didn't change. That's why we call this constant speed. Okay, remember that the difference between speed and velocity is that speed does not bother about direction, but velocity does bother about direction. So over in this case here, you could say that it is constant speed, but not constant velocity. Okay, why? Because direction changes, right? If your velocity direction changes, the velocity is assumed to is considered to have changed, right? So even though it's constant speed, we don't consider it as constant velocity, all right? Because the direction changes. This is number one. And then after that, since velocity changes, there is acceleration. Because as you learn in the kinematics chapter, we said that acceleration is rate of change of velocity. As long as velocity has changed, you have acceleration. So in the case here, your speedboat has changed direction. There is change in velocity. The velocity is not constant, so velocity is changing. When velocity is changing, there's acceleration. When there's acceleration, there's resultant force. When there's resultant force, that it is not in equilibrium. Okay, so therefore, it's not possible. Okay, now maybe I rewrite it another way for you. There is acceleration. If you want to, you can just write something like this. There is resultant force, therefore not possible to be in equilibrium. Okay, so this one is definitely not possible. As long as you change direction, you will have velocity change. You have velocity change, you have acceleration. You have acceleration, you have resultant force. You have resultant force, you do not have equilibrium. Okay, so this is answer choice C. Number 19, we just did that question last week. So this one, I'm just going to skip that. Then after that, we move on to the next page, page 7. Okay. Now, which pair of forces act only as a couple on a circular object? So this one is something that we've done quite recently, also last week. We mentioned that if you're talking about a couple must be a pair of equal opposite forces separated by distance. Let me open up the notes. Network energy power. That time, sorry, not work energy power, forces, density, pressure. That time we mentioned that a couple must be a pair of forces, a pair of equal opposite forces whose line of actions do not coincide. In other words, equal but opposite direction in force but separated by distance. So there were a few examples that we did before that to identify what is a couple, so we can apply it here. So when you look at this one, which one is wrong? This one is actually going to be correct because you see equal opposite force separated by distance. This one is correct. But you look at B, C, D, you will see that they're wrong. This one, not same magnitude. This one, wrong direction. Should be downwards and should be F. It should be like this. And then this one, for C, equal magnitude, no. It should be F. Are they opposite direction? Yes. Are they separated by distance? Yes. But the only thing wrong about it was that it's not equal magnitude. And then this one is definitely wrong because they are not opposite directions. Okay. Not in opposite direction. But right, this one should be something like this. Okay. Same magnitude, but not opposite in direction. So it should be something like this. And also separated by distance. The only answer choice that says that it's a couple is A. Okay. Right, so this one is okay. Then go to page question 20. Question 20 will tell you that the diagram shows the cross-sectional area of an Olympic-sized swimming pool that's filled with water is not drawn to scale. The density of water is 1000 kg per meter cube. What's the difference in pressure between X and Y? Okay, so the difference in pressure between X and Y, this one, generally what you will say here is this. Now, P equals to H rho G. This one is normally for pressure due to liquid. Okay, you may have also learned that P is equals to F over A, right? And then you also learn that P is equals to H rho G. But when do you know which one to use? Normally, P equals to H rho G is when it concerns liquid, when you're talking about pressure due to liquid. So over here is a swimming pool, it has water. You want to find the pressure due to water, which is in other words, pressure due to liquid. You will tend to use P equals to H rho G. All right. So they want you to find the difference in pressure between X and Y. This one you can actually just use pressure at X minus pressure at Y, it will be Hx rho G minus Hy rho G, which in turn becomes Hx minus Hy rho G. Hx minus Hy is basically this portion here, which is equals to 2.35 minus 2, giving you 0.35 meter. Okay. Hy is this one. Hx is this. So you find the difference between the two. So this one will be 0.35 meter times with 1000 times with 9.81. So what you're going to get is something like this. You're going to get 3.43 times 10 power 3 Pascal, 3.43 kilopascals, because the answer is in kilopascals. So answer is B. Okay. So this one is okay. And then for 14, which statement best describes a couple? So this one is just basically just talking about definition of a couple. So we'll go through each of them one by one. If you look at answer choice A, they say that it is a pair of forces. A pair of forces equal in magnitude acting opposite directions, which produce rotational motion but not translational motion. Translational motion is linear motion. Okay, when you hear the word translational motion, it is referring to linear motion. Okay, this is actually the definition of couple, because if you remember the steering wheel example from last week, we have a force F here, and then we have a force F here. This is a couple because it's a pair of equal opposite forces separated by a distance. Okay, so this force F here causes a rotation clockwise. This force F here causes a rotation clockwise. Both of them are in the same direction. So overall, they give you a rotation like this. All right. But you see, this F is equal opposite to this F. So there is no resultant force. Therefore, no acceleration and hence no motion. Rather than saying no resultant, no acceleration, maybe it's just better to say that there's no resultant force, hence no linear motion. Okay, right? So it is correct to say that a couple will only give you rotational motion, but not translational motion, no linear motion, because you see they are equal opposite in the first place. You're going to end up with zero resultant force. You're never going to move. All right, so the answer choice is actually A. All right, B, a pair of forces equal magnitude acting opposite directions which produces translational motion but not rotational motion. This is the direct opposite. It's wrong. You should have rotational but not translational. Then C, a pair of forces equal magnitude acting in same direction. This is wrong. Answer choice D, a pair of forces equal magnitude acting in same direction. Again, this is wrong. Okay, so answer choice is just A. This is again definition of a couple. Right, then I clear this one off. Okay, for the next page again, 15, you have a cross-shaped structure. Wait on, let me just see something else again. Let's do more on moments. I'll just skip that one. I want you guys to look at page 11. All right, just have a look at page 11. This is November 15 P22. Okay, define moment of a force. Moment is the product of force and perpendicular distance between the force and the pivot. Is a definition that you can see inside your notes. It is the product of force and perpendicular distance of the pivot from the line of action of the force. Or if you want to shorten your answer, just write product of force and perpendicular distance of the force from a pivot or to a point, whichever you want. Okay. So this one is part A. The one I want to do is the one that talks about the moment calculation. Okay, so now they tell you you have an arrangement for lifting heavy loads as shown in figure 4.1. Okay, this is what they show you. A uniform metal beam AB is pivoted on a vertical wall at A. The beam is supported by wire joining NB to wall C. The beam makes an angle of 30 degrees with the wall, and the wall makes an angle of 60 degrees with the wall. The beam has length 2.8 meters and weight 500 Newton. A load of 4,000 Newton is supported from B. The tension in the wire is T. The beam is in equilibrium. Okay, keyword equilibrium. And also another keyword is uniform beam. Uniform beam here will mean that the weight is exactly in the middle of the beam itself. All right. Now, so here they ask you, by taking moments about A, show that T is 2.1 kilonewton. All right. So when you look at this question here, by right again, there should actually be three forces. One force here, the tension T, actually four, sorry. There's tension of the cable on the rod, there's the weight of the rod, there's the load that is supporting, and there's also another force at the wall, the force that the wall exerts on the rod. Okay, so right now the question makes things simple for you. This force here, you do not need to consider because they ask you to specifically take moments about that point. Okay, so this force here is no longer, it's not considered. All right, so they say take moments about point A and show that the moments about point A is equals to 2.1 kilonewton. Okay, now from here, you want to find the moments caused by the forces, the 500 Newton, the 4,000 Newton, and this one. You can do a number of things. If let's just say right now you want to take this thing as it is to find the moment, you cannot do so because you don't have the correct values. You see, moment is force times perpendicular distance. Okay, moment is force times perpendicular distance. If I ask you for the force T, the tension T, is perpendicular distance, this is your pivot, okay? The perpendicular distance between your force T and your pivot is actually this one. Okay, so recall that I mentioned to you, if you want to find out what is the perpendicular distance, just draw a parallel line passing through the pivot. You'll be able to easily see it. So it's going to be this line here at 2.8 meter. But then what about the 500 Newton and the 4,000 Newton? For the 500 Newton force, your perpendicular distance will actually be this one. For the 4,000 Newton, your perpendicular distance will actually be this one. Okay, so right now, although you know the forces, you do not know the perpendicular distance. So what you will have to do is that you need to resolve the distances. Okay, so there's one way to do this. You resolve the distance, giving you this. You see, this one is using resolution of your distance. This one is 30 degrees. Your entire length of your beam is 2.8 meter. So you can actually choose to resolve your distances. This is like how you resolve your vectors previously. If you want to get the horizontal component, this one, if I shift it here, is actually opposite to my angle. So it should be sine. It will be 2.8 sine 30. Okay. Now this one here, the other part here, for the 500 Newton, it is this one here. Okay. This one, again, because it's opposite to your angle, it will be some sort of sine. But the distance you use is going to be this distance. It will be this distance times sine 30. But what is this distance here? This distance is actually half of this. And this distance here is half of 2.8. Your weight is acting right in the middle of your beam because it's a uniform beam. Okay, so it should be acting in the middle of 2.8. So this length here is actually half of 2.8. Sorry, it's getting very messy here. All right, this part here is half of 2.8. So if you want to find this distance, it will be half of 2.8 times with sine 30. That's why you get this. All right, this is the distance, the perpendicular distance of your 500 Newton force. This one is the perpendicular distance of your 4,000 Newton force. So from here, this one, you can actually find out your moments already. All right. This one is you do resolution of distance. There's another way in which you can also do this. Other than doing resolution of distance, you can do resolution of forces instead. What I mean by that is that rather than resolving your distance like the ones you see on the right, you resolve your forces, which is shown on the left here. Okay. So what you can do is this. Okay, the T here, you don't need to do anything because you know the perpendicular distance, you can straight away find the moments. The ones that you want to resolve is the 4,000 Newton and the 500 Newton. Okay, so to resolve your forces, this one you have to look at it a bit. Now, this one, if you look at your angles now, this part here forms a zigzag, right? If this one is 30 degrees, this one ought to be 30 degrees. And then for this one also is no difference. It should be 30 degrees also, because what you learned in maths was that if you have two parallel lines, this one, whatever angle is here, will be the angle here. So you're trying to see that relation here. Okay, you try to see that relation here, that's why you get this 30 degrees here, 30 degrees here, and 30 degrees here. Okay, so from there you try to resolve. I want to resolve the forces into two perpendicular directions. One that is like this and one that is like this. Okay, this one, if I shift it here, it is going to complete my triangle. It's opposite to my angle, so it's 4,000 sine 30. Now this force is going to be by right 4,000 cos 30. But because you see my pivot is here, it will pass through the pivot. So I don't really want to bother about this. Okay. Then I move on to the 500 Newton force, which is this. I know I can resolve it to this direction as well as this direction. This one, if I put it here to complete the triangle, is again opposite to my angle, so it's 500 sine 30. This one here will be 500 cos 30. But again, you see, because it passes through the pivot, I don't consider this. All right. So the moment calculation that I would use will only be due to this force and this force and this force. Right? All this I have the perpendicular distance already, because you see, if I rub everything off, for this one, the perpendicular distance is just going to be 2.8, because if I try to draw a line parallel passing through the pivot, this is clearly my perpendicular distance. And then if I talk about this one, my perpendicular distance will actually just be 1.4, because this is half this distance here. All right, this is the weight. The weight is acting in the middle of the beam. So if this length is 2.8, this length is 1.4. Again, the perpendicular distance, if I draw a line parallel to the pivot, parallel passing through the pivot, this is my perpendicular distance. Okay, so from there I can find my moments. So you can choose to do whichever you want to find the moments. In my case, I use resolution of the distances, the ones that I showed you here just now. That's what this working here is, right? It's 500 times 2.8 divided by 2 sine 30 plus 4,000 times 2.8 sine 30 minus t times 2.8 equals to 0, giving you this. Okay, it's basically this one, basically. This one gives me clockwise movement, therefore it's positive, therefore it's positive. This one gives me anti-clockwise movement, therefore it's negative. That's what I'm adding here. Okay. If you don't want to do this, as I mentioned to you, you can always do something like a shortcut, where you say clockwise movement equals anti-clockwise movement. So in other words, it will just be this over here and this over here. You get back the same answer. All right. So you get the answer as 2.1 kilonewton. That one is your tension T. Now calculate the vertical component of tension T. So if you're okay with that, we go back up again. You already found the tension T as 2.1 kilonewton. The tension T is this one. It is 2.1 kilonewton. They want the vertical component. This one can be resolved into this and this. You have TV and TH now. T vertical, T horizontal. But specifically we want this one. So what you can say here is that just now, if you recall the zigzag thing here, if this one is 30, this one must be 30, and this one is right angle 90. So 90 plus 130, sorry, 90 plus 30 gives you 120. This one gives you 120. But you know that the angle for a straight line like this is 180 degrees. So 180 minus 20 will give you 60 degrees here. So what you want to do is that you resolve the tension T into this component. Because this component is adjacent to the angle, it will be cos. So it will be T cos 60. 2.1 kilonewton times cos 60, giving you that value there. Okay. Yeah, this question is a bit messy to see, okay, but this is a good question to test your understanding of what is perpendicular distance and how to work through different diagrams. There's actually more examples of it in your structure, but we Can't do all of it in one shot today. All right, so this one is 1. Then we go on to the last part before we take a break. Okay, now state and explain why TB is not equals to the sum of the load and the weight of the beam, although the beam is in equilibrium. So basically what they're asking you is this. You see your TB, the vertical force, is actually 1060 Newton. Okay, let's just say 1060 Newton based on your answer. So they're asking you right now, why is TB not equal to the load, sum of the load and weight of the beam, although the beam is in equilibrium? If you look at the two forces here and here, the weight of the beam and the load, these two added up will give you 4,500 Newton. So the question here is telling you this beam is in equilibrium. Why isn't this one the same as this? Because under equilibrium, your sum of vertical forces must be 0. So right now they're asking you right now, why is this not the same as this one right now? Because if it is equilibrium, this force must be equal opposite to this, so that there's no resultant force. So the thing is that there is another force here. This force plus this force will be equals to this, so that your vertical force is 0. Okay, so you have to make reference to a force at that unknown. You have to make reference to the force at point A there. There is a force there. So that's why your answer was like this. There is an outward vertical component of force at A. That outward force at A plus TV is equals to the sum of your downward force. Okay. Right. So this one should be it. Okay, now it's 5:35 p.m. We just take a short break and we resume at 5:45 p.m. Then after that, maybe I'll start on your new chapter, work, energy, and power. Okay, right. So let's take a short break. Okay, right. So let's resume right now to our worksheet. Okay, have a look at page 1 of the worksheet that I just gave to you. Yangji, I think the admin would have sent to you the worksheet too, along with the notes, all right? So you have the worksheet already. If you don't have it, just let me know. Okay, right. Look at page 1, question 15. The first question here. They tell you you have a uniform meter rule that is pivoted at the 34 centimeter mark as shown. The rule balances when a 64 gram mass is hung from the 4 centimeter mark. What is the mass of the meter rule? Okay, so usually for questions like this, some keywords you need to identify from the get-go. This one is a uniform meter rule. So that means the weight is at midpoint. Okay. This one is if it's a uniform meter rule, that would mean that the weight is at midpoint. So since this is a meter rule, it has 100 centimeter, your weight is going to be acting here at the 50 centimeter mark. All right. Your weight is equals to mg. All right. Now, this is one force acting on the rule, but what are the other forces acting on the ruler? You have one force here, and you also have another force here. Okay. This one is due to your 64 gram mass. This one here is actually due to your string tension. Okay. Right now you see here, your ruler is suspended by a string. your ruler presses down on the string presses back up on your ruler. Okay, so all these forces that you see here right now is actually the forces acting on the ruler. The force 64 gram downwards, the tension of the string, and the weight W. Okay, now the force exerted by the string is unknown. The weight is also unknown. Okay, so there are two things here. Now, since this object is balancing, that means this one is in equilibrium. Okay, so no resultant force, no resultant moment. Because the thing here is that they say the rule balances when the 64 gram mass is hung from the 4 centimeter mark. It already implies the object is in equilibrium. There will be no resultant force and no resultant moment. So right now, what does the question want? The question actually wants you to find the mass of the meter rule, which is taken from here. Okay, so what you can do now is that you say sum of moments is equals to 0 because this object is in equilibrium. But which point should you pick as your pivot? So just now I mentioned to you, you tend to pick the point where you have an unknown force that passes through. So right now, this force is known, this force is unknown, this force is unknown, but this one is what you want to find. This one is not what you want. So this unknown force is unnecessary. You pick this point here as your pivot instead. You pick the 34 centimeter mark as your pivot because this unknown force here passes through that 34 centimeter mark, the pivot there. You don't need to consider the force inside your calculation. So taking moments about the 34 centimeter mark, okay, sum of moments is equals to 0. So T doesn't need to be considered already, all right, because it passes through this pivot. So T passes through pivot, so no moment to consider. Don't bother about this. You only need to consider the two forces here. Now, the weight will cause a rotation. Let me use a blue color here. The weight will cause a rotation clockwise. This mass 64 gram will cause a rotation anti-clockwise. Okay, so if you consider going clockwise as positive, this will mean that mg times with the distance, the perpendicular distance is going to be this one. What's the distance here? Is 50 minus 34, giving you 16 centimeter. This is 16. Then minus the weight here is giving you clockwise moment, so it's positive. The 64 gram mass is giving you anti-clockwise moment, opposite to your sign convention, so this is negative. So you're going to have a negative sign here. This one will be 0.064, change to kg, multiply with g, multiply with your distance. The perpendicular distance here is 4 centimeters. This one is not at the 0 mark, it's at 4 centimeters. Your perpendicular distance will be 34 minus 4 equals to 30 centimeters. So this one will be 30. Okay, so this one will be 30 equals to 0, right? So you notice a few things. The G will cancel off. All right. Now, I left this as centimeter because you see this part here, because this part here being 0, if I bring it around, this one will be m, this one will be 16m equals to 0.064 times 30. This 16 is in centimeter. This 30 is also in centimeter. The units will actually cancel off. I didn't change this to meter. By right, normally when you do your calculations, you will change your centimeter to meter, right? But here right now, I actually did not change it to meter because you see, this side here being 0, that will end up giving you something like an expression like this. The centimeter units for both sides will actually cancel off. So it's fine to just leave it as centimeter, all right? Because the units will cancel off. So right now what you have is this. You try to solve, m would be equals to 0.064 divided by 16. Sorry, 0.064 times 30 divided by 16. You're gonna get 0.12 kg. So this one is going to be 120 grams. Okay. So your answer for this is that the mass of the meter rule is 120 grams. Okay. Now, if you're not comfortable with leaving this in centimeter, you can also always change it to meter. All right, but eventually you'll come to the same conclusion. If this one is changed to meter and this one is changed to meter, the units will still cancel off. So you're basically doing some extra work for nothing. Okay. And you can actually omit the G also because you eventually be able to see that the G's will actually cancel off. Because once you put it here, 16 mg and 0.64 g 30, the G's will cancel off. So actually there's a shortcut here that you can use. Centimeter, just leave it in centimeter is fine. Omit out the G is fine because eventually, due to the fact that there's a 0 here, it will cause certain things to cancel off. The G will cancel off, the centimeter will cancel off. All right. So eventually, it makes your life easier. Okay, now for question 16, the diagrams here represent the systems of closed planar forces acting at a point. The length of the force vector represents the magnitudes of the forces. Which system of forces is in equilibrium? So when you say that something is in equilibrium, I mentioned to you, the only two things that will always come to mind is no resultant force and no resultant moment. Okay. Right now, how would you know that which one of these is in equilibrium? Okay. You won't really use this criteria. The part where we say no resultant moment, you won't use this over here because you don't have something that you can turn. Instead, you would use this criteria, no resultant force. Now, I mentioned to you no resultant force in any direction. So that means that sum of fx will be 0, sum of fy will be 0. So how do you apply it here? The question already mentioned to you that the length of the force vectors here represent the magnitude of the forces. So how do you know which of this is going to be in equilibrium? Now, the key to do this question is to resolve the diagonal forces. If you look at part A, this can be resolved into this and this. Now, notice that this one will balance this one will balance this one. So this one has no resultant force, isn't it? So this one could be in equilibrium. Now, if you look at the part B, part C, part D, you do the same thing again for the forces that are diagonal. If you look at this one can be resolved into something like this, as well as something like this. Whereas this one can be resolved into something like this, as well as something like this. Okay, now you see that the horizontal forces, this could balance this one. But then when you look at it vertically, this length plus this length is clearly not going to be the same as the downwards length, the downwards force. So here you have resultant vertical force cannot be in equilibrium, because if you add these two lengths together, it's clearly longer than this. So this one cannot be equilibrium. So you do the same analysis for the rest of the questions. You will see that this one resolve, it will become something like this. It will become something like this. And then if I do this one and I resolve it, it will become something like this, as well as something like this. Okay. Now again, same thing as before. You could say that this vertical force will balance off this vertical force. But then when you add this length and compare with this, it doesn't seem to be the same. Okay. These two are not equal opposite. So this one you have resultant force, so resultant horizontal force. Okay. So this is one part. So you do the same analysis again for the remaining thing. This one will be something like this and something like this. This one will be something like this and something like this. Okay. So for this one here, you can clearly see that this and this are not the same. I mean, if you try to draw it out properly to scale, this and this will not be the same. Okay. So this one you would have resultant horizontal and vertical force. So all these three has resultant force, not in equilibrium. Your only answer is part A. You can clearly see that they balance each other off. Okay.